Okay, lesson number 7 continues with the inverse of a relation. So when we're looking at the inverse of a function, there was 3 ways that we looked at in determining the function. We can take a set of ordered pairs and reverse the coordinates. So instead of writing it as an xy, we revert it as a yx. We can use the graph and we can reflect it about the line y equals x. So we can draw that mirrored line and then reflect it over that line. And then if we have an equation, we interchange the x and the y variables and then solve the equation for y. So some relations are functions and some relations are not. So the inverse of a relation which is not a function can still actually be determined. So if we look at this class example, we have a relation x minus 3 squared plus y squared equals 9. This is the equation of a circle. The circle has a center at 3 and 0 and a radius of 3. So the question is, describe how to use the graph of the relation to draw the graph of the inverse. So how would I use the graph of my first picture to draw the graph of the inverse picture? So go back up to the top where it gave you the 3 ways to draw an inverse. How do I do it when I'm given a graph?
To the y equals x.
Right. So I reflect and y equals x. So the first thing that I'd like you to do is draw me a circle that has a center at 3 and 0 and a radius of 3. So my circle has the center at 3 and 0 and a radius of 3. So all I'm doing is I'm basically drawing 4 points that are 3 units above, below, to the left, and the right, and then I'll join those 4 points with a smooth circular line. And that is kind of what my circle is going to look like. So now if I go to draw the inverse of this, I would start off with my reflection line. Which would be right here. And then what I would do is I would take my points that I kind of came up with, those 4 points, and those would be the points that I would reflect. So this point here, which was 0 and 0, is going to stay exactly where it was. This next point right here that I had that was at 3 and 3 will stay at 3 and 3 because when I inverse it, I still get the same thing. This point here, which was at 6 and 0, is going to become 0 and 6. And this point that was at 3 and negative 3 would become negative 3 and positive 3. And then my center, which was at 3 and 0, is going to be 0 and 3. So now if I join these 4 points with my smooth curve, there's my circle. And if I look at the 2 circles and I look at that reflection line, I can see that the green circle is a reflection of the blue circle. So that's how I could do this given the graph. How can I use the equation to write the inverse function or the inverse relation?
Change x and y.
So interchange x and y, and then solve for y. So if I look at my equation, instead of x minus 3, I have y minus 3 squared plus x squared would equal 9. So how would I solve or isolate the y variable? Subtract x squared. So y minus 3 squared will equal 9 minus x squared. then what would I do? Square root both sides. So y minus 3 would equal the square root of 9 minus x squared. And it would be the positive and the negative square root. And then my last step would be to add 3. So because I'm adding 3, I'm going to put the 3 out in front. 3 plus or minus the square root of 9 minus x squared. So we actually kind of did D and E together. This is the equation for D, and then E was solving for Y. You can verify the sketch using your graphing calculator. I'll let you do that on your own afterwards. Question F says state the domain and the range of the relation and the domain and the range of the inverse. So if I look at my original, so that was my circle in blue. What is the domain of the circle? What are my possible x values? 0 to 6. And I can use square brackets, and I can put it into interval notation. What would the range be? -3 to +3. And again, I could put it as interval notation with my square brackets. And then I'll do the inverse in green. So if I look at the green circle, what is the domain of the green circle? And what is the range? 0 to 6. And then the last question is, does this agree with the second and the third bullets in the review at the top of the page? So if we look at the top of the page, the second bullet says the range of the inverse is the domain of the original, and the domain of the inverse is the range of the original. The domain of the inverse is the range of the original. The range of the inverse is the domain of the original. Does that agree with the bullets? Yes, it does. So it agrees with bullets 2 and 3. So what I want for you to do for practice is questions 1 and 2. Thank you. Okay, so continuing on with writing an inverse, on the last class, we looked at ways, or the last couple of classes, we looked at how we can do the inverse of a relation. We can reverse the coordinates of a set of ordered pairs. So instead of writing, if the original function is xy, the inverse function would then be the pair y, then x. We can reflect the line, the graph in the line y equals x. And then in the equation, we can interchange the x and the y values and then resolve the equation so that it's a y equals. Things to remember, the domain of the inverse was the range of the original, and the range of the inverse was the domain of the original. The inverse of the function may or may not actually be a function in itself. So if we look at the next page, it looks at using function notation to write an inverse. If a function has an inverse which is also a function, then we can use this function notation. So function notation can only be used when I'm dealing with a function. Okay? So if I look at, I don't think it was the example down at the bottom of the page, or sorry, this one. The inverse function was the one that was in green. This is not a function. So this is an inverse relation. I would not be able to use the function notation for it. But the last class, I think we had a couple that were still a function when we inversed it. So if we have a function, the notation that we can use is it looks like f to the power of -1. And we read it as the inverse of f of x. So f inverse of x, or the inverse of f of x. Some textbooks don't actually make the distinction, and they use that inverse function for every inverse. With our curriculum, we designate that inverse notation for only functions. Okay? So the steps, if I have, because in order for this, or when this starts off, you're starting off with f of x equations. So let the f of x be equal to y, then interchange the x and the y variables, solve for y, and then if it's a function, replace y with f inverse of x. Okay? F inverse of x is the notation used for the inverse when the inverse is a function. F inverse of x does not mean 1 over f of x. And that's where the negative exponents can start to mess us up, because we're used to being told that 3 to the power of -2 is 1 over 3 squared. But f inverse of x is not equal to 1 over f of x. This is a reciprocal function. This is an inverse function. They are two different functions. So they don't mean the same thing. Because we're not looking at this as being an exponent. We're looking at it as being a notation. So if we look at the class examples, it asks to determine the inverse of the following. So I have f of x equals 2x minus 3. So instead of writing this as f of x, we write it as y. Y equals 2x minus 3. And then we inverse, or we interchange the x and the y variables. So I get x equals 2y minus 3. I want to get y by itself, so I add 3 to each side, and then divide by 2. So if I split this apart, I get 1/2 x plus 3/2 if I divide both terms by 2. This might actually be a better way of writing this, because what kind of equation do I have here? What kind of function is this? Pardon? Y equals mx plus b. It's a linear function. And this linear function starts at 3/2 and it's going up over by 1/2. So is this going to be a function? A straight line is a function. So instead of y, I would write f inverse of x. Okay, so I'll give you a moment. I want you to do B. So if we look at B, I would start off by writing it as a y equals x cubed plus 4. Then I interchange the x and the y, so that now I have x equals y cubed plus 4. Subtract by 4. And to get rid of the cubed, I would cube root it. Now when I cube root this equation, do I have to put a plus minus in front of it? So when you cube root a number, can you get a positive and a negative answer? No. If I cube root 27, I only get 3, because 3 times 3 times 3 is 27. If I cube root negative 27, then I would get negative 3. Is the cubed root of x minus 4 a function?
Yes.
Yeah, if I graph it, it kind of looks like, so the x cubed plus 4 kind of goes like this. So then the inverse would kind of go, let's see, look at my coordinates being like that. It kind of goes like that, right? Something like that. Is that a function? Yes.
So to tell if it's a function, you just graph it on the calculator.
Sometimes you have to graph it. Really, when you get something that is not a function, it's because it had 2 possible outputs for the single input. In this case here, if I put a number in for x, I'm only going to get 1 possible answer. So where you see 2 possible answers sometimes is when you've got a square root, or a 4th root, or a 6th root, something that I could have 2 possibilities. Sometimes with an absolute value function, when you find the inverse might not be a function. So you just think about the values that you're putting in and whether or not you're going to get 1 or 2 outputs. So because this is a function, I can replace the y with my function notation, f inverse of x. And all that does is tell whoever's looking at this equation that this equation was the inverse of something else. That's the purpose of putting that in there. So now if we look at the next example, f of x equals x squared minus 4. So if I graph this function on the grid and then determine the domain and the range. So if I go back to what I know about quadratic functions, they're usually, or they can be written in the form of a times x minus p squared plus q. Well, p in this case would be equal to 0, because there is no p value. Q would be equal to negative 4. So I have a vertex at 0 and negative 4, and then it's going to open up. The other thing that I could look at, x squared minus 4, when would that equal 0? What value of x would make that equation equal 0? 2. 2 squared is 4. 4 minus 4 would be 0.
Or negative 2.
And negative 2. So now I have some coordinates. I can now graph this. And there's my graph without having used the graphing calculator. What's the domain of this function?
Negative 2. Oh, wait.
What can x be? X can be any real number. What about y? Greater than or equal to negative 4. And y can also be a real number after that fact. So now if this right here, where it says determine x equals f of y, and then solve for y, this is asking you to determine the inverse. That's what this notation here means. Determine the inverse. So I would have y equals x squared minus 4, which would then become x equals y squared minus 4. Add 4 to each side, and I get x plus 4 equals y squared. And then what would I do to get y? Square root it. And when I square root it, what do I have to do? Plus or minus. So when I go to graph this, if I think about these 3 points and inverse those 3 points, So instead of -2 and 0, I have 0 and -2. This point here, which was 0 and -2, now becomes -2 and 0. And then this last point, that was 2 and 0, sorry, I've got that drawn wrong, don't I? Yeah. 2 would look like this. There we go. Oh, still have it drawn wrong. 2, 2, 4. There we go. Okay. Because this is -4 and 0, right? Or 0 and -4 would become -4 and 0. -2 and 0 becomes 0 and -2. 2 and 0 becomes 0 and 2. So there's my inverse. That's better. So if I go to state the domain and the range of the inverse, what's the domain of this inverse? What are my possible x values? -4 to infinity. And what's the range? -infinity to infinity. And does that follow the rule that we did in A? The domain became the range became the domain. Is the inverse a function? No. So the inverse is not a function. But could I make it a function? So could the domain and the range of the original function of f be restricted so that the inverse was also a function? So the problem that happens is when I take the inverse, I get two possible outputs because of this plus or minus. But if I could restrict it so that I only got one output, it would work. If I say, you know what, I'm only going to choose the positive x values. So if I said in here, x has to be greater than or equal to 0. If I did that, then my y value would be that y has to be greater than or equal to 0. And that's the graph that I would get. This graph in red, is it a function? Because there's only one output. So I could restrict the domain of f to be x is greater than or equal to 0. And then when I did that, the range or the inverse would then be a function. Don incorrectly determined the inverse of a function defined by y equals the square root of x minus 3. Are there values of x that are not defined for this equation?
X equals. And it can't be negative.
What can't be negative? X can't be negative. So is it everything less than 0? Less than 3. Because if this is 0, what do I get underneath the square root? I get a -3, and I can't have a negative number. So my domain has to be greater than or equal to 3. If my domain is greater than or equal to 3, when I put 3 into this equation, I get 0. The square root of 0 is 0. If I put 4 into this equation, I get the square root of 1, which is 1. If I put 7 into this equation, I get the square root of 4, which is 2. So my y values are always going to be what kind of numbers? Positive numbers. So y is going to be greater than or equal to 0. So with that said, when I go to do my inverse, what's going to happen to my domain and the range? They're going to switch. So in my inverse relation, my domain is going to have a restriction where x has to be greater than or equal to 0. So if I look at the inverse, I interchange the x and the y. So I get x equals y minus 3, or square root of y minus 3. I want to get y by itself. So I need to get rid of the square root sign. How do I do that? Square both sides. So x squared would equal y minus 3. And then add 3 to both sides. And I get x squared plus 3 equals y. But x has to be greater than 0, greater than or equal to 0. And y would be greater than or equal to 3. So then when I go to graph these two equations, if I graph y equals the square root of x minus 3, I get a graph that looks like that. When I go to graph the inverse, instead of 0 and 3, I would have 3 and 0. If I reflected about this line, or sorry, I had those backwards. This was the original. That was my square root one. This is the... There we go. This was my y equals x minus the square root of x minus 3. When x equals 3, y equals 0. When x equals 4, y would equal 1. When x equals 7, y would equal 2, and so on. And then the inverse would be half of the parabola. So the inverse function so because this half of the parabola is a function, I could rewrite this as f inverse of x equals x squared plus 3. But I would have to include those restrictions on the domain and the range. So we always have to go back to finding the restrictions. So when you're writing a function, be aware of what the restrictions are in that function. If I look at class example number 5, it goes back to class example 2a, where we had f of x equals 2x minus 3, and the inverse of that function was 1/2 x plus 3/2. And that's just from the previous page. So what we're asked to determine is the composite function f of the inverse of f of x and f inverse of f of x. So if we start off with this first one, this is f of f inverse of x. So that means it's f of 1/2 x plus 3/2. So where I see x in my f of x equation, I substitute in. So I get 2 times 1/2 x plus 3/2 minus 3. What is 2 times 1/2 x? 1x. And 2 times 3/2? 3. And x plus 3 minus 3? just x. If I do the other composite function, f inverse of f of x becomes f inverse of 2x minus 3. So in this equation where I see an x, I substitute, so I get 1/2 times 2x minus 3 plus 3/2. So 1/2 times 2x is x, and 1/2 times negative 3, and x minus 3/2 plus 3/2 equals x. So another way that I could show two functions are inverses of each other is when I take the composite function, I would get the answer of x. So if I gave you two functions and I said without going through, without interchanging, how would you prove these two functions are inverses of each other without doing the other three methods? You could take the composite of the functions to show that they equal x. If they equal x, they have to be a composite, or they have to be inverses. So question 5, 7a and b, 8b, 9, and then 11 to 14.